Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video we're going to continue the discussion of carbonyl chemistry. In particular, we'll be focusing on addition reactions of aldehydes and ketones. Now, before you watch this video, I do have several suggestions in order for you to make the most of this one, and that is watching the video Recognizing Nucleophiles, Bases, Electrophiles, and Acids, the alkene addition reactions video, the video Alcohol, Ether, and Epoxide reactions, and, as usual, the organic chemistry reactions problem-solving process. Prerequisites aside, let's go ahead and get started. When we think about the aldehyde and the ketone functional group, what should first come to mind is that electrophilic carbonyl carbon. That's the carbon that is double bonded to the oxygen. This is an electrophile, and it's the site where nucleophiles can attack, and it's used for addition reactions, reduction reactions, and oxidation reactions. The electrophilic carbonyl carbon is something that has been mentioned in other videos before. We're going to add some layers of knowledge, and that is we're going to discuss the carbonyl oxygen and the carbonyl pi bond, which both can serve as weak nucleophiles and bases. With the pi bond, we can simply say that addition occurs across both sides of the bond, just like is the case with any addition reaction, such as additions with alkenes. The pi electrons here versus an alkene, however, are polarized by the electronegativity difference between the oxygen and the carbon, and these pi electrons are involved in resonance. With the oxygen, what we say about it is that it can initiate addition reactions by attacking acids or sometimes even electrophiles, often making the carbonyl carbon more electrophilic. Let's talk a little bit more about the electrophilicity of the carbonyl carbon. Due to both inductive and resonance effects, the carbonyl carbon bears a partial positive charge and is susceptible to attack by a nucleophile. You can see the two resonance structures drawn on the left and the resonance hybrid drawn on the right. Although we have the major contributor being the resonance structure that does not have a charge separation, we can see that with that other resonance structure, we do have a little bit of charge separation in that resonance hybrid. And of course, with the electronegativity difference, oxygen pulls electrons away from that carbon, contributing to its positive character. When we compare different aldehydes to different ketones, we can also discuss how they affect the electrophilicity of that carbon. That carbon can be stabilized by electron-donating groups, and we've encountered R groups before. They donate electrons to the carbonyl carbon the same way they donate them to carbocations through hyperconjugation. In addition, bulky groups adjacent to the carbonyl carbon decrease electrophilicity due to steric effects. In other words, they crowd it and prevent it from being attacked by a nucleophile. These factors explain why formaldehyde, which is that molecule on the left, is more electrophilic than other aldehydes, shown in the middle, and why aldehydes are more electrophilic than ketones, which have two R groups. And last, due to the basicity of the pi bond and the oxygen in aldehydes and ketones, these carbonyls can easily be protonated by a strong acid. What this does is it places a positive charge on the molecule that is stabilized by resonance. So you can see that OH plus, and you can see the resonance structure of it that puts the positive charge on the carbon. The net effect of protonation is increasing the electrophilicity of the carbonyl carbon so that it can be attacked by weaker nucleophiles. When students are first learning carbonyl additions, it can often get very confusing because of the way that textbooks often present the reactions. Not only are there a ton of addition reactions of aldehydes and ketones, but many of them have some nuances, which makes it difficult to keep track of them all. Therefore, it's best to think about their similarities to other reactions that you may be already familiar with before trying to learn all of these individual reactions. Just like alkene additions, carbonyl addition reactions can be broken down into two general categories: additions initiated with and additions initiated without a strong acid. On the bottom of this page, I show the general mechanism for carbonyl additions with and without a strong acid. Once you start going through all of the individual reactions, you'll begin to see why it's so powerful to break down these reactions into these two simple types. Let's start by discussing the carbonyl addition reactions initiated with a strong acid. While aldehydes and ketones can react with a variety of nucleophiles, sometimes the nucleophile just isn't strong enough to react with the electrophilic carbonyl carbon, at least initially. In these cases, an acid catalyst is needed to protonate the carbonyl first, making the carbon more electrophilic and therefore more susceptible to nucleophilic attack, even by a weak nucleophile. In this general reaction mechanism shown, you can see three distinct steps. The first step is protonation. You take that nucleophilic and basic oxygen, those lone pairs on it, and you simply react that with the positively charged hydrogen of some generic acid HA. And what that does is it creates a resonance-stabilized cation. And like we discussed, because we have a cation, we have increased the strength of that positive charge. In other words, we increased the electrophilicity of that carbonyl carbon. Next, we have the nucleophilic attack. So our weak nucleophile, often neutral, the lone pairs on it are simply going to attack that positive carbon. Finally, we're going to have a deprotonation step. Because we had a weak nucleophile, it likely had an extra hydrogen on it, making it positively charged. So what's going to happen is the conjugate base of our acid is simply going to come in and deprotonate it, giving us our final addition product. Now, after the addition product is created, and depending on the reaction conditions, the reaction may or may not be complete at that point. For example, in the reaction to create an acetal, which we'll cover later in this video, the addition product will continue to react, following the same principles learned in previous units regarding reactions of alcohols. Regarding acid-catalyzed addition reactions that can stop after the addition without any additional steps, we have hydrate formation and cyclic hemiacetal formation. We also have a couple of reactions that have additional steps after the acid-catalyzed addition is complete, and that is the acetal formation reaction as well as the thioacetal formation. Let's go over these reactions next. In our first acid-catalyzed addition, we're going to discuss hydrate formation. And of course, we're going to go to our problem-solving process, and we're going to list everything we know about this first reactant, this aldehyde or ketone. What do we know about it? Well, we know that it has an electrophilic carbonyl carbon, and at that carbonyl carbon, we can do addition, reduction, and oxidation reactions. We also know that we have a nucleophilic and basic oxygen, so we can also initiate addition with that site. When we look at what's on the reaction arrow, we have HA, so we know we have a strong acid, and we also have H2O, which is a weak nucleophile and a weak base. So because we have this strong acid, it looks like we're most likely going to do an acid-base reaction to initiate this addition. So now we can draw our mechanism. And as usual, we start by drawing an arrow from the negative to the positive. So we take one of the lone pairs of this oxygen and we attack this hydrogen, and that breaks the HA bond. That gives us a protonated oxygen, which of course has a resonance structure that we can draw. The resonance structure will clearly show that we increased the electrophilicity of that carbonyl carbon. Now, even though oxygen is a weak nucleophile in water, because we have a stronger electrophile, that oxygen in its lone pairs can attack the stronger electrophile. This adds the water molecule to the carbonyl. Of course, now we have a positive formal charge on that oxygen that we just added. So to remove this, we're simply going to draw the conjugate base, or the A- that was formed when we deprotonated the acid, and it is going to attack one of these hydrogens, making that OH neutral. The resulting product, which has a carbon bonded to two OH groups is called a hydrate. How much hydrate you form at equilibrium is dependent upon the electrophilicity of the starting aldehyde or ketone. If you start with formaldehyde, you're going to get a very high percentage of hydrate concentration in equilibrium, over 99%. This drops for other aldehydes to just around 50%, and it drops dramatically to just over 0% when you have a ketone. In other words, this reaction is not something that you see very regularly. For the next several addition reactions, there are some new functional groups that are important to learn and be able to identify. We're going to start with the hemiacetal. And the hemiacetal is what happens when we do an addition to an aldehyde or a ketone with some OR group that came from an alcohol. So notice the carbon is now bonded to an OH group and an OR group. A cyclic hemiacetal also has a carbon bonded to both an OH and an OR, but the OR is actually part of a ring. Cyclic hemiacetals are very important to understand, especially when you start learning about carbohydrates. Next up, we have an acetal. And an acetal takes the OH group that was present in the hemiacetal and also converts that into an OR group. An acetal is a protecting group of aldehydes and ketones, but their use as a protecting group will be covered in a different video. We also have cyclic acetals, and a cyclic acetal simply has the two OR groups connected to each other. Some courses also teach you about thioacetals and cyclic thioacetals, and these are different from your corresponding acetals simply by swapping out the oxygen for a sulfur. Again, being able to identify these different functional groups is going to be a very important skill for you in organic chemistry, so familiarize yourself with these functional groups as soon as possible. So now let's go over how to create an acetal. And once again, we are talking about additions of aldehydes and ketones in the presence of a strong acid. As usual, we're going to start with our problem-solving process. So we're looking at this and we have a ketone. And the ketone has an electrophilic carbonyl carbon, where we can carry out addition, reduction, and oxidation reactions. And we also have a nucleophilic and basic oxygen, and we can initiate additions there as well. When we move on to the next step of the problem-solving process and look at what we have on the line, I have HOTS. Now this is the way that I write TSOH. I found that students, when they say TSOH, don't instantly recognize it as an acid, and they think that it is a base because they see the OH. It's actually a very strong acid with a pKa of about -7. So again, I write it as HOTS. That way it's a little more obvious that it is an acid. So we have a strong acid there, and in addition to that strong acid, we have two equivalents of an alcohol. Alcohols, of course, have two lone pairs, but they are neutral, which makes them weak nucleophiles and weak bases. Now that we've identified all our functional groups and reactive sites, we can make a prediction as to what's going to happen. And I see a base with an acid. So let's initiate our reaction by drawing an arrow from the lone pairs on the oxygen over to this acidic hydrogen and breaking this hydrogen-oxygen bond. This, of course, creates the resonance-stabilized cation with a stronger electrophilic carbon. Because we have a stronger electrophile on the carbon, the weak nucleophile, or the alcohol in this case, can now do a nucleophilic attack at that site. So we're going to draw our arrow from the lone pair on the oxygen over to that electrophilic carbon. Students often make a big mistake when drawing the product of this step. If you notice, all we did was we drew an arrow from an oxygen to a carbon, and all that does is it creates a single new bond. So I'm going to draw this new bond in blue. Notice that is the only arrow that we drew. That means this oxygen is still bonded to the two things it was bonded to before, and that is a hydrogen and an ethyl group. Because there are three bonds and still a lone pair on here, we have a positive formal charge on the oxygen. A lot of students will try to either attach only the oxygen with the R group or only the OH group. But again, we're only drawing one arrow, which signifies the creation of a bond. None of the other bonds break. So this is the intermediate that we get. In the next step, we take our OTS negative. In other words, we take the conjugate base of our original acid, and we use that to deprotonate the oxygen. This gives us our neutral hemiacetal intermediate. So far in this reaction, it has pretty much mirrored the general mechanism of an addition to an aldehyde or ketone with a strong acid catalyst. However, there are a few problems with what we just did. First, a ketone is a lot more stable than a hemiacetal, so there's not really a driving force to create a hemiacetal. In fact, equilibrium heavily favors the ketone, and all of these steps are in fact reversible. So in order for this reaction to actually happen, we need to continue it. And luckily for us, we did put two equivalents of the alcohol on the line. So what we're going to do next is not technically an addition reaction. We've already done the addition, but it's the reaction of essentially that OH group, and it acts a lot like the reactions of alcohols. Remember that we're in an acidic environment with this HOTS. So what's going to happen in the next step is this strong acid is going to protonate that OH group. Why can it do this? That's because the OH has lone pairs on the oxygen, so it has nucleophilic and basic properties. You may be wondering, why wouldn't we just protonate the other oxygen? And the answer is, you do, because this is an equilibrium reaction. So if we were to go in the reverse direction, the other oxygen would be protonated, and the reaction would essentially be reversed. But that does not mean we cannot move in the forward direction and have the oxygen on the OH deprotonate HOTS. When we do that, of course, that is going to give us an OH2, which is a good leaving group. Now we have the positive formal charge on the oxygen. And it is going to leave, which leaves behind a resonance stabilized cation. And once we have this cation, we can bring in that second equivalent of alcohol that we had originally. So the lone pair on that alcohol will attack that positive charge on that carbon, and that's going to add on our second OR group, except we still need to keep on that hydrogen because once again, we are not breaking any bonds when we draw that arrow. We're simply creating a new one. Of course, we don't like that positive formal charge on that oxygen, so once again, we are bringing that conjugate base, OTS negative, to remove or deprotonate that oxygen, giving us our final acetal product. Now, there are a lot of additional notes that I want to bring to your attention on hemiacetals, acetals, and thioacetals. First, the acid TSOH is widely used when creating acetals. However, some resources don't put a specific acid on the reaction arrow and choose to use a generic H+ or an HA instead. So just because you don't see TSOH does not mean you're not creating an acetal. Second, and I already mentioned a lot of this when I went over the mechanism, hemiacetals are much less stable than aldehydes and ketones, and also they're less stable than acetals. That's why two equivalents of alcohol, or a diol, are needed to take this reaction to completion. If only one equivalent of alcohol is used, essentially we're going to get no product because equilibrium will strongly favor the starting material. Unfortunately, some resources and professors omit the two equivalents from the reaction arrow, making this reaction much more difficult to identify. On the other hand, there's something called a cyclic hemiacetal, and these are stable, and they can be created via an intramolecular addition reaction, and I'll show that next. Third, I did not show the mechanism to create a thioacetal. However, it is identical to the mechanism to create an acetal, except we use a thiol instead of an alcohol. I already mentioned that the reaction is reversible. In dehydrating conditions, that is, if we remove water as it's created, we remember that the water is actually a leaving group in one of the steps, and therefore is a product. So if we remove it as it's created, according to Le Chatelier's principle, we're going to shift equilibrium to the right, creating more product. So in other words, if we remove water as it's formed, we're going to drive this reaction to the right to get more acetal product. However, in excess water, we're going to drive the reaction to the left, and that's called hydrolysis. And last, the acetals are used as a protecting group of aldehydes and ketones, as previously mentioned, and the specific details regarding their use as a protecting group are covered in another video. Let's talk next about cyclic hemiacetals. As I mentioned, a cyclic hemiacetal is stable and can be isolated, so we don't need to go all the way from the aldehyde or the ketone to an acetal if we can get a cyclic hemiacetal in the middle. And how we do this involves an intramolecular reaction. So let's take a look at the molecule that we have right here. As usual, we're going to start with the problem-solving process, and we're going to identify all of the functional groups on this original molecule. And I noticed that I have a primary alcohol, a secondary alcohol, and an aldehyde. I've gone ahead and listed everything I know about these functional groups. For the alcohol, we have lone pairs on the oxygen, which means that the oxygen is nucleophilic and basic. We also have a slightly acidic hydrogen on both the alcohols, and we have the oxidizable carbon. On the aldehyde, of course, we have our electrophilic carbonyl carbon, and we can do addition, reduction, and oxidation at that site. Also, we have the nucleophilic and basic oxygen with its lone pairs, and we can initiate an addition at that site as well. Moving on to the reactant on the line, we have HA. So we have a generic strong acid. So what it looks like we have to do is use one of the oxygens as a base to do an acid-base reaction. Now, all oxygens are capable of interacting with that strong acid, so which one are we going to do? Well, it is the aldehyde oxygen that's going to react, because that's going to give us the most stable product because it's resonance stabilized. So we're going to react this oxygen with the acid. And of course that gives us our resonance stabilized cation. To save space, I just drew the resonance hybrid. At this point, you should be very comfortable saying that because we have this cation, the electrophilic carbon is more electrophilic than it was before we protonated the oxygen. This allows weak nucleophiles, like alcohols, to attack that position. So we're actually going to attack with the lone pairs on this alcohol that's the furthest away. Why do we attack with that one and not the closer one? Well, that has to do with the fact that we're making a much larger, more stable, six-membered ring with far less angle strain than if we attacked with the other oxygen, which would make a four-membered ring with high angle strain. So let's go ahead and figure out how to draw this cyclic intermediate. Anytime we do an intramolecular reaction that creates a ring, it's a good idea to number all of the atoms from where you attacked to what did the attacking. So here, I'm going to label that carbonyl carbon with the 1, and I'm going to label out 2, 3, 4, 5, and 6, all the way to that oxygen that did the attacking. This tells me that I'm going to have a 6-membered ring. I'm going to go ahead and draw that 6-membered ring now. Now that I've drawn the 6-membered ring, I'm going to go ahead and number the corresponding atoms. Of course, my drawing is not complete because I haven't finished drawing all of the extra groups on the molecule. So let's go ahead and do that now. At the 6th position on the oxygen, I still have a hydrogen bonded to it. I didn't break that bond, so I still have an OH, and this is going to have a positive formal charge. Also at the 3, I still have an OH group, and there's no reason why it shouldn't remain on a wedge, so I'm going to keep that on a wedge. Now I do want to point out one thing that I didn't draw, and I'll draw it in there now. Because I drew the resonance hybrid, I should probably indicate that somehow these electrons went up to the oxygen, but because I did a hybrid, it's kind of weird to use a full arrow, so I'm just kind of using this dotted arrow, a convention I just made up right now, to show that we are moving those electrons from that kind of double bond up to the oxygen. Now I have the proper 6-membered ring. Of course, we don't like that formal charge on that oxygen, so we're going to use our conjugate base of that acid to deprotonate the oxygen, giving us a neutral product. No reaction is complete unless we follow step 4 of the problem-solving process, which is check for stereochemistry, carbocation rearrangements, and resonance. Here, we did have a trigonal planar group that got attacked, so we could have attacked it from the front side or the back side, which means that this OH should be on a wedge or a dash. So we can have either version. This product is a cyclic hemiacetal, and cyclic hemiacetals are very important to carbohydrate chemistry. So the reaction can stop here. However, if we did want to convert this into an acetal, we could. We would just need to treat it with more acid and one more equivalent of alcohol. And that's what that bottom reaction is going to show. Here we're just going to continue the mechanism to create an acetal. So the oxygen on the hemiacetal is simply going to attack the hydrogen on the acid. That will give us a protonated hemiacetal, where we have an OH2 group that is now a good leaving group. So what is it going to do next? It's going to leave. The question may come up, why did we protonate that OH group on the hemiacetal rather than the alcohol OH group? And the reason is because once we draw the cation that was left behind, we'll see that it was resonance stabilized. The hemiacetal is going to form that resonance stabilized cation, where the alcohol, if it left, would just give a secondary carbocation, which is less stable. After this cation forms, a weak nucleophile, like the CH3OH we have here, can attack that position. That's going to add on the OHCH3 to that position, which then, of course, to get rid of the formal charge on the oxygen, we're simply going to use that conjugate base to deprotonate it, giving us the neutral acetal. Once again, we should check for stereochemistry, carbocation rearrangements, and resonance. And because we had that trigonal planar cation, again, we can have this group added as a wedge or a dash. Now that we've talked about the carbonyl addition reactions that were initiated with a strong acid, let's talk about the ones that we do not need a strong acid to initiate. If a nucleophile is strong enough to react immediately with the electrophilic carbonyl carbon of an aldehyde or ketone, a strong acid catalyst is not needed to initiate the reaction. However, this does not mean that an acid can't be present or that an acid is never used in these reactions. It simply means that the acid isn't used in the first step. There are many strong nucleophiles that can initiate carbonyl additions, including carbanions and organometallics, hydride delivery agents, amines, and hydroxide. Here is the general mechanism for a carbonyl addition reaction initiated without a strong acid or initiated with a strong nucleophile. In the process, you can see two distinct steps. First, we have a nucleophilic attack at that carbonyl carbon position. This sends the double bond electrons up to the oxygen and puts the nucleophile on to that carbon. The second step is protonation, and the molecule that we use to protonate varies depending on the reaction. Sometimes it's water, it can be an alcohol, or it can be an acid source. So this mechanism, as you can see, it's actually much simpler. It's only 2 steps. It's much simpler than the one where we use an acid to start the reaction. The following carbonyl addition reactions follow this above mechanism very closely. Hydrate formation with a base catalyst, cyanohydrin formation, reduction with hydride delivery agents, and addition with carbanions or organometallics. Some carbonyl addition reactions involve a modified addition mechanism where the addition product continues to react, yielding unique products. And these are addition of primary amines to form imines, addition of secondary amines to form enamines, and the Wittig reaction to form alkenes. Once again, we're going to explore hydrate formation first, but this time we're going to use a base catalyst instead of an acid catalyst. The same general principles still apply. We have decreasing carbonyl carbon electrophilicity as we add R groups and replace hydrogens with them, and therefore we have decreasing hydrate concentration at equilibrium the more substituted we are at that carbonyl carbon. The mechanism is pretty much going to follow exactly what we just did with that general mechanism. Here we have an aldehyde or a ketone, and we have this electrophilic carbonyl carbon. And we know that we can do addition, reduction, and oxidation at that site. We also have the nucleophilic and the basic oxygen, and of course we can initiate addition at that position. But now we have OH minus and water, so in other words we have a strong nucleophile and base. And because we have a strong nucleophile and base, we're going to attack the electrophilic carbonyl carbon directly. We don't need to protonate first. So we're simply drawing our arrow from our negative to our positive, and of course this sends the double bond up to the oxygen. And that is going to give us a single bond O negative, and we just added on this OH right here. The next step is simply protonation, so we're going to take our water, and that O negative is going to attack the hydrogen, giving us back our base catalyst. And you can see here that we have our hydrate product. It's a very simple reaction. In our next reaction, we're going to explore cyanohydrin formation. So once again, we start with the problem-solving process. And here we have a ketone, and we have the usual things that we talk about with ketones. So we have the electrophilic carbonyl carbon, where we can do addition, reduction, and oxidation. And we also have the nucleophilic and basic oxygen, where we can initiate addition from. What's on the line is interesting. We have NaCN, which is really just Na plus and Cn negative being a strong nucleophile. And then we have HCl. HCl is a strong acid. However, what it's going to do in this case is give us HCN, which is a weak acid. So here, we're not actually protonating the oxygen. We're still going to use the Cn negative as a nucleophile. So here's the notes that we have. And in this first step, like I said, we do not protonate first. We're going to take this Cn negative, and we're going to use this to attack the electrophilic carbonyl carbon and send this pi bond up to the oxygen. That, of course, is going to give us this O negative, and we just added this Cn group. And like I said, that HCl is going to interact with some Cn and give us the weak acid HCN. And HCN is actually our proton source for the next step, which is protonation. So this O negative is going to attack the hydrogen on HCN, and that's going to give us our final cyanohydrin product with an OH group and our CN, or our nitrile group. And of course, we did have a trigonal planar starting material, so when we attacked with that CN nucleophile, we could have attacked from the front side or the back side, which means we have a stereogenic center here where either the OH or the CN can be on wedges or dashes. Our next reaction is a reduction with hydride delivery agents. And the hydride delivery agents that we have available are LiAlH4, sometimes abbreviated as LaH for lithium aluminum hydride, and NaBH4, or sodium borohydride. They work the same way. Lithium aluminum hydride is just a stronger source of hydride. So to start this reaction, once again we have our ketone, and we have the following things that we know about the ketone. Whether we have NaBH4 or LiAlH4 on the line next is not that important because they're going to do the same thing to the ketone. In both cases, we have a positive ion, either an Li plus or an Na plus, with an anion, an AlH4 negative or a BH4 negative. Also in both cases, the hydrogens are more electronegative than the atom that they're bonded to, either the aluminum or the boron, which makes the hydrogen capable of acting like hydride or H negative. That's where our hydride source comes from. So what I like to do when I see NaBH4 is simply write BH3 with an extra hydrogen coming off and a negative formal charge. And then I take that bond between the hydrogen and the boron, that's our nucleophile in this case, and that's going to attack the electrophilic carbonyl carbon, sending the bond up to the oxygen. Of course, what that does is it gives us an O negative, and we just added on a hydrogen to that carbonyl carbon. And the next step we're going to take our alcohol, CH3OH, and this is going to be our source of hydrogen. So we're going to protonate this oxygen by attacking the CH3OH. That, of course, is going to give us an OH here. We don't need to draw the hydrogen because we don't draw hydrogens on carbons. And once again, when we consider stereochemistry, this could be on either a wedge or a dash because we could have attacked it from either side with that hydride. Our next reaction is an addition with organometallics. We have two choices for organometallics reacting with aldehydes and ketones. We have the Grignard, which is the RMGBr, and we have the organolithium, which is the RLI. Both of these are strong organometallics, and the negative charge lies on the carbon bonded to either the magnesium or the lithium. That's because the metals, magnesium and lithium, again, are very electropositive, so they donate their electron density. So, in other words, these molecules act like carbanions. They're strong nucleophiles and they're strong bases. So let's analyze the reaction we have shown here. We have a ketone, and once again, we can list everything we know about the ketone regarding its electrophilic carbonyl carbon and its nucleophilic and basic oxygen. And then on the line, we have an organolithium, a strong organometallic, which once again behaves as if it were a strong nucleophile or a strong base. So what we're going to do is we're going to initiate an addition reaction with this organolithium. And what we have is the bond between the carbon and the lithium, that's where the electrons lie, attack the electrophilic carbonyl carbon, and once again we send those electrons up to the oxygen. So what happened here is we broke the bond between the carbon and the lithium. That's what drawing that arrow meant. And because the carbon is where we had the electron density closer to, we just added that CH3 group to that carbonyl carbon position. Of course, we don't like having the negative charge on the oxygen, so that's when we bring in water as our hydrogen source, and simply we do a proton transfer where the O negative attacks that hydrogen, giving us our product, where we have an OH and we have this additional CH3. Now, normally I would say check for stereochemistry, and once we check, we realize that we do not have a stereogenic center in this particular reaction, because two groups are the same. We have two methyl groups on that central carbon, so this is, in fact, our final product. The next two carbonyl addition reactions involve reacting the aldehyde or ketone with either a primary or a secondary amine under mildly acidic conditions. And by that, I mean the pH should be around 4 to 5. This reaction doesn't quite follow our normal pattern of addition, and also we get some extra steps which have the oxygen actually end up leaving as a leaving group. Because of these seemingly weird things that happen that aren't in line with what happens with other addition reactions involving a stronger nucleophile, students often forget that this reaction exists. In fact, I often joke with my students that this is the most forgettable reaction of organic chemistry, and I tell them, you're probably going to forget this when it shows up on a test. And sure enough, they almost always do. Anyway, here's how it works. As is almost always the case, I'm going to start with the problem-solving process, and of course we have a ketone with its electrophilic carbonyl carbon and its nucleophilic and basic oxygen. And of course we can do addition, reduction, and oxidation. On the line, we have RNH2, and this is a primary amine. Notice the nitrogen has a lone pair on it, which means that it can serve as a fairly strong nucleophile or base. We also have mild acid with this reaction. I'll get into why we need mild acid a little bit more later on in the video. But what we're going to do, we're going to take that lone pair on the nitrogen, and we are going to do an addition by attacking that electrophilic carbonyl carbon, exactly like you would expect to happen. And of course, what this does is it gives us our O negative, and we just added on this N with an R group and 2 hydrogens. Of course, nitrogen doesn't like having 4 bonds, so we're going to put a positive 1 formal charge on that. What happens next is pretty familiar. We have our mild acid, and the O negative is going to deprotonate that acid, giving us a neutral oxygen, but we still have this issue where we have a nitrogen with a formal charge of +1 on it. So here's where things start to get a little bit different. Now, we're going to take that A negative that we had, and this is going to do another proton transfer. We're going to take a hydrogen off and create what is known as a carbonyl amine, and that is where we have an OH and our NHR bonded to the same carbon. The carbonyl amine is very similar to the hemiacetal in that it's not very stable, and at this point, if we do not continue the reaction in the forward direction, it is simply going to reverse and take us back to the starting material, because every step here is reversible, just like every step is reversible in the formation of an acetal. So what's next shouldn't surprise you if you're familiar with that acetal reaction, and that is we're going to use our HA and we're going to protonate something. Now the nitrogen and the oxygen both have lone pairs. So if we protonate the nitrogen, we're simply going to go in the reverse direction, and this is equilibrium, so of course some of that's going to happen. Or we can protonate the oxygen, and that's going to drive this in the forward direction. And of course, every step in this reaction is reversible, so I will draw the double arrow, and I'll continue to do it. So in the forward direction, we're going to take this lone pair and the oxygen, and we're going to attack the hydrogen on our mild acid, and that's going to turn this into an OH2+, which of course is a great leaving group, and we still have this NHR, and I'm going to draw in the lone pair for a reason. And that's because in the very next step, the leaving group is going to leave, and when it leaves, the lone pair on the nitrogen comes down and forms a double bond. This gives us another intermediate called an iminium ion, where we have a double bond N, and it's still bonded to an H and an R, so it has a formal positive charge. In the next step, we're going to bring in that conjugate base again, so we're going to take our A negative, and we're going to use that to deprotonate the iminium ion, and that's going to put the lone pair back on the nitrogen. That's going to give us our final product, which has a carbon-nitrogen double bond, and an R group is still bonded to that nitrogen, and this product is called an imine. Notice the similarities in our final product to the final product when we created an acetal. With the acetal, the original oxygen on the carbonyl was completely removed. It left as water. Here, the original oxygen also left as water. And with the acetal, we replaced it with 2 bonds to OR groups. Here, we replaced it with a double bond to a nitrogen. With the addition of a secondary amine, we follow mostly the same process, with the final step being the only difference. So once again, we are going to attack this electrophilic carbonyl carbon with the nucleophilic nitrogen. That's going to send that bond up. That's going to give us our first intermediate with an O negative and our NHR2+. Again, what we're going to do next is we're going to use HA, and that's going to be our first proton transfer step, where the oxygen grabs the hydrogen. In our second proton transfer step, that conjugate base is going to deprotonate that nitrogen, restoring neutrality to the nitrogen. From here, of course, we're going to have yet another proton transfer step involving our mild acid, and the oxygen is going to grab the hydrogen. That creates the good leaving group, OH2, which is then going to leave, and the lone pair on the nitrogen is going to come back down and form a double bond. That, of course, gives us our iminium ion, and so far, every step in this reaction has looked identical to when we added the primary amine. The difference in the last step of this reaction, however, lies in the fact that when we use a secondary amine, we only have 1 hydrogen to take from it. So notice that this iminium ion does not have a hydrogen bonded to the nitrogen. So in order to get rid of the cation, what we have to do when we bring in our A negative in the last step is we have to remove a hydrogen from somewhere. So where are we going to remove it from? We're going to remove it from an adjacent carbon. Now, I can remove it from either of these adjacent carbons. However, the final product is likely going to be the one that forms the more stable double bond, very similar to Zeitz's rule for eliminations. So That's going to come in and remove the hydrogen on the more substituted carbon, and that's going to cause that carbon-hydrogen bond to break, forming a double bond, and that allows us to take the pi bond between the carbon and the nitrogen and move its lone pairs up to the nitrogen. This, of course, is going to give us our product with a carbon-carbon double bond adjacent to an Nr2, and we call this an amine, or an alkene amine. Of course, if we want to be really thorough here, we should definitely check for stereochemistry, and we would realize that if we do that, we do have the opportunity to get E and Z isomers. So I can also draw this way. And of course, if we wanted to remove the other hydrogen from the other side of the molecule, we could have had this amine instead. Like I mentioned earlier, the reactions to create the imine and the amine are probably the two most forgettable reactions in organic chemistry. Here are some additional notes on the imine and the amine formation, hopefully to help you remember them, because if you know more facts about them, perhaps you'll remember the reaction better. Mild acid means a pH range of about 4 to 5. We want that because in the presence of too much acid, or in other words, having too low of a pH, all of the amine would be protonated, and this would make it unable to act as a nucleophile. On the other hand, in the presence of too little acid, the oxygen would not be able to be protonated the second time, preventing the formation of the leaving group. Another note is that a secondary amine only has one hydrogen, and that's why the final proton transfer step must occur at a carbon, creating the double bond adjacent to the nitrogen, as I showed in the last slide. And our final note is that just like in the acetal formation reaction, both of these reactions to create the imine and the enamine are reversible. And in dehydrating conditions, the reaction is driven to the right to create more imine or enamine. Again, this is because water is one of our products. It leaves as a leaving group, so if we remove water as it's formed, according to Le Chatelier's principle, we're going to create more product, driving the reaction to the right. In excess water, on the other hand, the reaction is driven to the left, and just like with acetals, we call that hydrolysis when we go back to the starting material in excess water. The final carbonyl addition reaction that we're going to cover is called the Wittig reaction. And the Wittig reaction is a carbon-carbon bond-forming reaction that looks noticeably different than the other carbonyl addition reactions. And that's because it's actually a different mechanism overall. It's actually a 2+2 cycloaddition reaction, which technically doesn't look like the other additions. Regardless, the reaction mechanism can still be explained using familiar principles covered throughout this video, even though they might not be technically accurate. The end product of the Wittig reaction is the conversion of a carbonyl into an alkene. In other words, that CO double bond is turned into a CC double bond. On the very right-hand side of the page, I have what is called the Wittig reagent. And you can see that there is a resonance structure for the Wittig reagent. On the left, we have what is known as the Aldehyde representation, and an aldehyde is a molecule that has a negative charge adjacent to an atom with a positive charge. The resonance structure, of course, shows a double bond between that phosphorus and the carbon next to it. In the actual Wittig reaction, it makes more sense when drawing the mechanism to represent the Wittig reagent as an aldehyde. Now, before we continue, I do want to make one note. This video only shows the Wittig reaction mechanism itself. It does not cover the creation of the Wittig reagent, nor any of the other nuances associated with the reaction. The Wittig reaction itself is covered in much more detail in another video. That being said, let's see if we can work our way through the problem-solving process to figure out exactly how this reaction works. Here we have a ketone, and of course, as we've been saying this whole time, we have an electrophilic carbonyl carbon, where we can do addition, reduction, and oxidation reactions. And also, we have that nucleophilic and basic oxygen, and I do want to point out that we also have the nucleophilic and basic pi bond, which we kind of can just treat as a unit of excess electron density. And we can initiate addition reactions from that site as well. When we look at the Wittig reagent, we should notice two things about it. First, we have a strong nucleophile. That is where we have that negative charge. However, we also have a positive charge on the phosphorus. So we also have an electrophilic phosphorus. So what's interesting about this is both the carbonyl and the Wittig reagent have a nucleophilic and an electrophilic site. So the arrows we're going to draw are fairly interesting. The negative charge on the Wittig reagent is going to attack the electrophilic carbonyl carbon. What normally happens during this nucleophilic attack is the pi bond gets moved up to the oxygen. However, in this case, the pi bond is not going to move up to the oxygen, but it's going to move up to attack the electrophilic phosphorus. Let's see if we can piece together in a drawing what happened. What I'm going to do first in this drawing is draw the oxygen on a single bond rather than on a double bond because we used those pi electrons. Now I'm going to draw our two new bonds, and I'll switch colors to draw the new bonds in blue. The oxygen forms a new bond with phosphorus, and the carbon formed a new bond with the other carbon. However, the carbon that had the lone pair and negative charge on it, we never broke the bond between it and phosphorus, so we still have this carbon-phosphorus bond. In addition, that carbon is still bonded to a methyl group, and the phosphorus is still bonded to 3 of those pH3 groups. So what you can see here is that we formed a cyclic 4-membered intermediate. 4-membered rings, of course, are not very stable due to their high angle strain. So what happens next is we break 2 bonds to form 2 new pi bonds. So this carbon-oxygen bond is going to break, and the electrons are going to transfer between it and the phosphorus. And the carbon-phosphorus bond is also going to break, forming a double bond between the 2 carbons. This is going to give us a final alkene product that looks like this, and we'll get an OPPH3, a stable byproduct. So as you can see in this final product, we initially took that carbonyl carbon-oxygen double bond and we replaced it with a carbon-carbon double bond. And that is the Wittig reaction. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.